Hello, and welcome to lesson 31 of this introduction to calculus with Wolfram U. The topic for this lesson is average value of a function. So let's begin with a brief overview of the lesson. So let's say you have a list of numbers like over here, and you want to work out their average value. So of course what you do is just add the numbers and then divide by the number of numbers, which is 10 in this case, and get back the answer. But we also have a function called mean in the Wolfram language, which does just the same thing for you, and you get back the same answer. But now let's say instead of a list of values, you had a function like the one shown over here. So here's a plot of the function, and the question is, can we work out the average value of such a function? And the answer is yes. So here's some intuition. So let's say your function runs from A to B. So you break the interval into n subintervals, take a sample point in each subinterval, and then work out the average value like over here. Now, we won't rewrite it as a Riemann sum, so the n over here can be thought of as related to delta x, the length of each subinterval. So delta x is b minus a over n, and hence n is b minus a over delta x. So you can rewrite the average in a slightly different form, in which it's clear that if you now let n go to infinity, so you got very small subintervals, then what you get back is the integral divided by the length of the interval. So that's the average value of a function. It's the integral of the function over an interval divided by the length of the interval. So let's say in our example, if you want to work out the average value, you simply find the integral from 0 to 5 and then divide by 5 and you get back the answer. Okay, now a much deeper fact is something called the mean value theorem, which says that if you have a continuous function on an interval, then there is at least one number c in that interval such that the value of the function is equal to the average value. So that should remind you of the mean value theorem for derivatives, which did the same thing, but now for integrals over intervals and areas rather than slopes. So if you multiply both sides by b minus a, what you get on the left-hand side is just the area of a rectangle with height f of c and length b minus a, and the right-hand side is the integral. So here is a visual interpretation of the whole thing. So let's say this is your curve, and now you have the area under the curve, and that's a rectangle. Now there's a bit of area that's common over here, and then a bit over here which only belongs to the rectangle, and a bit that only belongs to the curve. And what we're saying over here is that the area of this rectangle is equal to the area under the curve. So that's quite a remarkable theorem. It's very deep and shows you how powerful calculus is. We have reduced the area under a curve to the area of a rectangle, which is the simplest thing one might think about in areas. Okay, so as an application, here's a function, and you want to find a value in the interval -2 to 3 such that the function value is equal to the average value over that interval. Now, because the function is continuous, it's a polynomial, so you can certainly apply the theorem, the mean value theorem. So let's say you want to do that, you solve the equation f of c equal to the average value, and when you do that, you get back an answer, and here's a plot which shows the point at which the average value is actually attained. So that's the mean value theorem in action. But the main point is that sometimes you can get more than one point at which the average value is attained. So here's an example where you have a function, you try and work out the average value and then work out the point at which you want to check whether the average value equals the function value. You get 2 points now, and here's a picture which says that you really have 2 points at which the average value is attained. So as an application of these ideas, here's the temperature for a city t hours after noon. You plot the temperature from 1 p.m. to 3 a.m. And the question is there a time at which the temperature equals the average temperature? And the answer is yes. Just solve the equation and you get back that C is about 8.57. That's in hours. So that means that at around 8:34 p.m., the temperature will be equal to the average temperature over the time period. As another application, let's look at a car on a highway. So here is the velocity of the car. Now you want to find the average velocity over the time period. So what you do is you simply integrate and divide by the time interval. So here's a plot which shows clearly that the average value is attained at two different points. So the average velocity is attained twice in the interval. And that brings me to the end of the lesson. But the main point for today is that with integration, you can find the average value of a function over an interval. And that average value is given by the integral divided by the length of the interval. The mean value theorem is a very powerful theorem which says that if you have a continuous function, then it takes on its average value at least once, could be more than once, but at least once in the interval. And of course, once you have this very powerful theorem, you can apply it to temperatures or velocities or all kinds of other physical phenomena. So you have a mean value theorem which tells you that the area under the curve is equal to the area of a certain rectangle. That's a very powerful theorem for calculus. So in the next lesson, we'll talk about the approximate values of integrals. But for now, do review this lesson, go over the idea of a mean value, and I'll see you next time. Thank you very much. I'll stop over here.